Hi everyone, I'm going to show you how to run Exotic as a first-time user. So this is the Exoplanet Transit Interpretation Code, which will take a folder of images on your Google Drive file system and fit it to a light curve for your target and then plot and analyze the light curve. So the first thing that we have to do is save a copy of this notebook on Google Drive, and that will allow it to be your own copy that you can edit. So I'm going to go to File, Save a Copy in Drive, and then it's creating a copy, and it will open a new tab with the editable copy of this notebook. And I'll close the original copy, and that way I won't get confused and accidentally run the wrong notebook. So the first thing to do is to give it permission to run on my Google Drive file system. It claims that it's mounted, but it's really not. It's only showing that because this is the output from last time this notebook was run. And when it created a copy, it copied also the output from the last time it was run. So it's not actually mounted, so I have to give it permission. And I'm going to click the little run thing in the upper left of the cell, and then this will give it permission. So I'm going to sign in and choose an account that I'm going to let Exotic have its way with, allow it to do what it wants to my file system. Some people prefer to run on a throwaway Google Drive account just for extra security. But then when I copy the code and enter it into this box, it will mount my Google Drive file system so it's actually mounted. And then I need to install Exotic and some other modules. So I'm going to run this cell. This downloads Exotic, a fresh copy of the code from GitHub where it's stored, and it installs everything that it's going to need to run the data on the virtual machine that this is running on in the cloud. So it's running on my Google Drive files, but it's running on a virtual machine, and that machine needs to have everything installed on it that needs to be installed for Exotic to fit a light curve from my files. You notice this is still running because the little circle's still going, and the Colaboratory logo up on the top of the tab is gray. And that's how I know that the notebook is running. And when it turns yellow again, I'll know that it finished, and this cell will also be finished. In general, all the code in these cells is hidden, but if I wanted to see it, I could double click the cell and see what it's doing. This is all the stuff that it's doing. If you don't want to see it, you right click on the left side of the cell and go to Form Hide Code. So you don't need to actually look at it. Also, the first line of this code suppressed the output, and normally there'd be a lot of gobbledygook that gets spit out as it's running to say like, yes, I installed it, etc. Okay, so now it's done running. And then we have to look up the target in the NASA Exoplanet Archive. We're going to run the sample data because this is first time we're looking at this Colaboratory. And so our target is going to be HAT P32B. So I'm going to click run, and I'm going to put HAT P32B as my exoplanet target. It isn't infinitely flexible about how I enter that, but it's somewhat flexible. So it figured out that NASA is going to want these little hyphens, for example, and that it wants it capitalized in space before the B. And then it went and looked on the NASA Exoplanet Archive and found the parameters. And all of these things are important for Exotic to be able to fit a light curve to the target. And you can see them if you go over to the NASA Exoplanet Archive. Right here, you could put in HAT P32B, and it'll show you the parameters that Exotic is querying if we enter the right target name. Let's see. Here's the target name that I guess they want for that. So NASA Exoplanet Archive, unlike this, is not flexible about hyphens and capitalization. There we go. So here are all the orbital properties of the planet and of its host star. And those are the things that Exotic needs to know about in order to fit a light curve to a folder of data where this star was imaged. So next thing, I'm going to let the collaboratory know what I want to do. And in order to do that, I need to tell Exotic where to find the images on my Google Drive file system. But what if I don't have any images there yet? So I'm on my Google Drive file system. Actually, I do. I downloaded the folder of sample data in advance. But I'm gonna say that I didn't do that. So I'm gonna rename this to sample data previous, because what the code will do is look in my Google Drive file system for a folder called sample data. And then if it doesn't find one and I'm running the sample data, it'll go ahead and download that from the GitHub. So, so I'm gonna run this cell. It says press enter to run the sample data. And that's what I'm gonna do because I'm a first time user. So I'm just gonna press enter and it's gonna go and get the sample data from GitHub and copy that into my Google Drive file system. And if I go and look now here, I have a new folder. It's called sample data and it contains within it the sample data, hat P32B there. Okay, so now what it's done is it went into that folder and it found the first image in the folder. It found 142 image files. So they were just taking images of this star and it didn't find any initialization files. But not to worry about because I don't even know what an initialization file is yet. I'm a new user. So it displays the first image in this series, and then I need to figure out where my target is in that image. And there are a number of ways to do that that are explained separately outside this notebook. But for now, I'll tell you my target is right here. That's the star in the middle of this field, whose light I'm monitoring as this program goes on. So I'm gonna put the coordinates X and Y. You don't need to worry about value, but I do need to put X and Y in as the coordinates of my target. And so they are here. And then I also need to enter coordinates of some comparison stars. There's outside this notebook explained how you pick comparison stars, but I'm going to, for the moment, I'm going to pick this one. And then also, let's see. So how about, I think this one would be a good one right here. And so I copy down those X and Y coordinates and I need double square brackets for those. So I'm going to put those in here like this. And I had them saved in advance so that you wouldn't have to watch me type them. And then we're ready for the next step. So it downloaded the sample data. It's got my coordinates in there, and it's going to run on this thing called an inits file, which it built for me based on my images. And so next we're going to run the fitting. This is going to take a while because it'll take kind of between 15 and 30 minutes, depending on my data, but I'm going to run it. You can see there was some previous output displayed in the cell from having run it before. So when I start it running again, that previous output goes away and will be replaced by the new output when it finishes. But we basically just have to wait. And when it's done, it'll display all the output and you can examine it and inspect it as below. So I'm going to pause this video while we wait. Okay, it's done, and it output some files, and unfortunately the files are, the images, you have to scroll up in the cell output, which has its own scroll bar in order to see it all. But the first thing is a field of view picture that shows my target circled. It will also circle any comparison stars if it used them, but in this case, it got the cleanest light curve without using any comparison stars. So it didn't even use one. And then here's the light curve. And this is the light from the host star. And you can see that it dips down when the target passes in front of it. Then it also shows this image of what are called the posteriors of the FIT. And the main thing that we're looking for here is that they make Gaussian bell-shaped curves. If they don't, then something might be amiss, or the data might be particularly noisy, but analyzing those is something that you can learn how to do outside this notebook as well. And then if I go and I look in my sample data folder and I look where the images lived, in that folder, I'll see a new folder titled Exotic Output, and this saves it outside the notebook so that I can look at it when I want to later. It has the final light curve. It has the final light curve in there. And so we already looked at that, the field of view plot. It also has this AAVSO file, and that's for the American Association of Variable Star Observers, so that you can upload your data to their database, and that will help them make it available to other astronomers to plan their observing campaigns, and also to NASA to optimize time on upcoming Space Telescope missions. So it's a great idea to go and join American Association of Variable Star Observers and make an account so that you can participate in this citizen science effort. There's some other files in there as well, some various ways of looking at the field of view of HAT P32. And then it also has this inits.json file. And that's the initialization file that the program made for me, that Exotic used to run my data. And so if I look at that, what's in there, I can see that it took those planetary parameters from the NASA Exoplanet Archive. So it's using those. And then it also specifies where on the Google Drive file system my images live. And that has this content drive, my drive prefix that Google Drive needs in order to have it on my file system. And then it saved plots in this exotic output directory. And that's the directory that I'm in right now. So all of the output stuff got saved in there by default. And so you can see if you wanted to run a new directory of images with your own initialization file, if you just look this stuff up and then you can specify your own, like if you have a different organization for your Google Drive, you could specify different paths, just remembering to include this content drive, my drive prefix in its files. And then here you see you need some other stuff, which it went and got out of my FITS headers for the sample data images, but which you would have to enter if you were running this program from scratch. So it needs the date of the observation, and then some information about the observatory, latitude, longitude. Remember that longitude west has this negative sign, and it's going to need a plus or a minus sign on both of those. And the elevation, and then some information about your filter. Some of those are in there by default, some are not. So if it's not stored in Exotic already, you have to put in the wavelength, the passband of your filter. You may or may not need the pixel scale, depending on whether that's already in your FITS headers or not for your images. So, so basically, if you wanted to do this on a new set of data, you could run this same code. I could run it again, and I wouldn't have to do the first two steps because it's already mounted and installed. But I could do it for, say, a new target, say WASP 43b. 43B. And then I could tell it to go and look in a different folder for my images here. So here, if I look in my drive, I actually have some data for this target, but it's not in a folder called sample data. It's in a folder called WASP43B. And within that folder, I have a number of different transits of this target that I want to run. So this is the first one of those images. So I would say instead, when I go to the let the collaboratory know what you want to do today step, I would tell Exotic where to find my images. Here, I made it so that you don't have to put the content drive, my drive prefix. I mentioned that in the text above. So I'm just going to put WASP43B, and then the first one of those image directories, 3239 KB95, 3239 KB95, and it'll go and find that directory of images, which already exists on my file system. It found 198 images in that directory. It also found 2 initialization files because I've run this previously, but it doesn't know which one of those to use. So it's going to make a new one for me anyway. It also takes a few extra seconds to display that image because it's a bigger image. It came from the Las Cumbres Observatory telescopes, but eventually it'll come up and it'll prompt me for target and ComStar coordinates, just as it did for the HAT P32B data. There we go. My target here is right in the middle of the field, and then I can pick some ComStars, and it runs exactly the same way as before. And when it's done, it'll make a folder called exotic output within that directory. And it'll put my output there. Unless, like, if I had just one initialization file in the directory, then it would run on that initialization file and put my output wherever I said to put it in the inits file. But since I had 2 and it doesn't know which one, it's going to make a new one and use that default output directory of exotic output. Anyway, this video is far too long, so I will stop it now. And thanks for watching.